Hi Tara, what settings did you use when you made the Zoom meeting? Because I thought you were already in here, but the second I joined, I was the host.
Oh, I made you an alternate host.
Like, because I did that last time with Amy, but she still had to wait for me to start the meeting. And like, even when she did, she wasn't the host.
Um,
Because if this works fine, then we only need one Zoom link.
yeah, I'm still the host.
Yeah, but like, I came here before you and I automatically was assigned the host.
Yeah, I mean, but I'm also the host. You know what I'm saying? So
Oh,
like if I go to your little ellipses on your video, I can withdraw your co-host permissions and stuff. And I have the option to make you the host. So I think as soon as I joined, I became the host. But you should still have hosting permissions.
yeah, I do.
Yeah. Then I think I could edit the settings and make this recurring for Mondays as well. And then we could just have one link. You prefer?
Okay, yeah.
Okay, cool.
And are we recording the meetings or no? Because I paused it when I joined.
Yeah, we will be.
Okay.
Oh, is it recording? Oh, yeah, it's recording now. I think when I joined, it automatically recording. So
Well, like when I joined, it started recording, so I just paused it.
yeah, but when I joined, it started recording again.
Oh,
Okay, so I will. Okay, so welcome everybody to Chemistry 118, Gen Chem Lab 2. My name is Tara Mooney. I'm a PhD student in organic chemistry in Bela Torok's group. So Victoria and I will be co-teaching this lab section. Victoria, would you like to introduce yourself?
hi, I'm Victoria. I don't know, I don't know what else I should say.
What lab are you in?
Um, Michelle Foster's group.
Okay, so Shelley Foster's group does like theoretical type chemistry, right? Yeah. Okay, so we will be co-teaching this semester. So let's get into the intro today. Okay, so let's start off with the materials you'll need for the lab. You will need the lab manual. The first few lab manual pages are on Blackboard for sure. If you need any of the lab manual pages, please contact us so that we can get those for you. It says you need a bound composition notebook. It doesn't need to be a bound composition notebook this semester because we are not collecting the notebooks as we usually do. Just make sure that you are writing all of your notes in one place for this class. So you will need to be submitting your pre-labs every week. You should have a graphing calculator or yeah, you can, so going back to the notebook pages, you can definitely type them. So that's a good question. Let me get back to that for a second. So for the pre-labs, you can type them. You can write them in a notebook and submit like a picture of them or a scan of them. However you can get that to us is totally fine. Okay, so for the calculator, we recommend for our science students that you should have a graphing calculator. If you don't have a graphing calculator, the next preferred would be a scientific calculator, but we are not doing anything more complicated than simple algebra, so any type of calculator should be fine. You will need some sort of computer for completing the assignments in this class. You will need to type up your lab reports. You will need to be making graphs and such. So try to get a computer if you don't have one. We will be using Microsoft Word and Excel. So students can get Microsoft Office for free on IT's website. So if you have not done that yet, you can. So Microsoft Office is kind of expensive. So if you get it for free through the school, then you'll just have it. If you get a new computer and you need to download it again, you should be able to. I believe I've downloaded it on several different computers. Okay, so obviously you'll also need something to write with, a blue or black pen. If you're doing everything on your computer, then I suppose you don't need a blue or black pen. All right. Okay, so lab rules. So even though we're not in the lab, I'm going to go over this with you because these are general requirements that you will need in the future in all of your lab courses. So labs will start promptly at their scheduled times. If we were in person, we would give like a certain amount of leeway. Usually we spend the first few minutes collecting all of the pre-labs. In that time, you do have some leeway. Safety goggles must be worn at all times. We are very serious about lab safety here at UMass Boston, as every university should be. So there's no eating or drinking in the lab. That is true in any lab setting, in academia, in industry, no eating or drinking in the lab. Proper lab attire must be worn. So my scientists, as you are getting into more advanced classes, you should get used to wearing pants every day, even in the summer, as well as closed-toed shoes. That is just a standard that you should just be getting used to. If for religious reasons you wear skirts, make sure that they are floor length. Okay, so chemicals in the fume hood must remain in the fume hood. So fume hoods are especially engineered to make sure that the chemicals we're using do not escape into the lab. So we want to make sure that we're not taking anything out of the fume hood that is especially volatile. Gloves must be worn when working with hazardous materials. So on the same note, we don't like you guys to have phones or anything in the lab, because if you are using your phone and chemicals at the same time, you're going to be able to transfer chemicals onto your phone and outside of the lab. So if you have, say in the future, you do have your phone in the lab, like a lot of us scientists do, you always want to make sure that you wear your gloves while you're using the chemicals and you take them off to use your phone or other devices, such as any instrumentation that is in the lab. You don't want to use gloves with any instrumentation. So we don't dispose of any of the chemicals in the sinks unless you are instructed by a TA to do so. For environmental purposes, we want to make sure that everything we put down the sink will not ruin our environment. So even salts and things, if they're too highly concentrated in our environment, that will cause some ecological issues. So even if it's a salt, sometimes we still want you to dispose of it in the proper waste receptacle. So be aware of everyone and everything around you. So for instance, even if you are done with your experiment and you feel like that you can take your lab goggles off, your lab mates around you may not be done working. And if they have some sort of accident that is too close to you, it could be a safety issue for you. So you always want to make sure that you are wearing your safety goggles in lab until everyone is done. Okay, so safety first. Okay, so another thing on the safety, we will be expecting all of you to watch the safety video on your own time, and make sure you take the safety lab quiz. I think we'll get to that again, but just in case, the safety quiz must be completed by next Wednesday. So watch the video and take the quiz. Both of those can be found in the course materials. If you took 117 with us before or just previously, it's the same safety video. Okay. So pre-lab notebook, what are we expecting for your pre-lab notebook? So it must be prepared beforehand. Like I said before, you can type them, you can write them, whatever, it doesn't really matter. So in order to prepare for the pre-lab, you should read the lab manual pages. So make sure you read the background information, make sure you're actually reading the procedure, everything like that. So that's all in the lab manual. If you want extra information, you can listen and watch the voice thread. So that is basically a secondary lab lecture for you guys to have. So what will be in the lab, the pre-lab? So you should have a 1 to 2 sentence purpose describing the purpose of the experiment. So for instance, today we are doing the limiting reagent experiment. And so an example purpose would be something like, the purpose of this lab is to determine the limiting reagent of a reaction between calcium chloride and sodium carbonate, and determine the limiting reagent at various volumes of the reactant, something like that. So that is a 1 to 2 sentence purpose. Next, you will need a brief list of the key concepts. So in this lab, we are studying studying how to figure out what a limiting reagent would be in a reaction using balanced chemical equations and stoichiometry. So the next part is you want to basically just summarize the procedure of what we're doing today. So that doesn't mean all of the steps. That means the overall concept of what we're doing. So today that would be something like we are starting with X and Y concentrations of calcium chloride and sodium carbonate, and we are varying the volumes, and we are going to weigh the amount of product made, and based on that we are going to determine what is the limiting reagent, something like that. So you don't need to go step by step by step. Okay, so also in your pre-lab, you should be preparing all the tables beforehand. So for instance, in the lab manual today, there is a nice table. So you want to make sure that that is prepared so you can just fill in all the data as you go. And then at the end of the day or the end of the lab, you'll write a summary about what you did in the lab or anything significant. So for instance, you would want to summarize like you were able to use stoichiometry to determine calcium chloride was the limiting reagent in certain conditions and sodium carbonate was the limiting reagent in other conditions. So just something really quick. Okay, so that is the pre-lab notebook. So lab participation and conduct. So basically virtually just show up to class and be prepared. If we were in the lab, this would also include making sure like you're following all of the lab rules. So if you consistently forgot lab goggles or forgot to put on lab goggles, that would be something that would count towards your grade. Or if you came in with like food or drink, things like that. But in a virtual setting, we don't really need to worry about those things. So as long as you are present and not disruptive, you will be a-okay. Okay, so lab reports. The lab report writing guide should be on Blackboard in the course library. If you follow the lab report writing guide, you should earn pretty much full marks on your lab reports. For those of you who are taking organic chemistry in the future, I would recommend saving the lab report writing guide, as the rubrics that we use are all based off the lab report writing guide. Okay, so there are 3 different formats for our lab reports. So we will have one long lab report this semester. Most of our lab reports will be short lab reports, also called abbreviated lab reports. Victoria, so Ariba is asking, the lab notebook summary is due at the end of every lab. Is that something you did in 117?
Yeah, I always had the due date set to 4:30, like when lab ends, but I think maybe we can leave it open until like 4:40, just so they have time to actually submit it.
Okay, yes. So yes, to answer your question, the summary is due at the end of the lab. Okay, thank you, Victoria. So the most of our lab reports will be short lab reports. They're also called abbreviated lab reports. So in the lab manual, at the end of the experiment, it will say which sections of the lab report you need to write. So we will go over this when we get to today's actual experiment. So each abbreviated lab report will require something different. And then finally, we do have a few labs that are worksheet labs, and those worksheets will be in your lab notebook. The lab reports will be submitted on Blackboard. The lab reports for the Monday labs will be due at 11:59 p.m. on Thursdays. The Wednesday lab, those reports will be due Saturdays at 11:59 p.m. So the short lab report for today's lab on the limiting reagent will be due this Saturday at 11:59 p.m. So when you are submitting the lab report, make sure it is in a PDF or document file. So Blackboard does not render Google Docs. So if you are working on a Google Doc as your main form of writing, you do need to make sure you save it as a doc file or convert it to a PDF before you submit. So late experiments do have a 10% deduction for each day they are late. And if the report is late by 5 days, it's no longer accepted. So if you have, if something happens to you, like you get COVID or whatever, something unexpected, please make sure that please make sure you email the person grading your lab reports that you might need some extra time. So we tend to be, pretty flexible about that if you are running into some issues. So that's another thing I want to point out. Even though that you guys are in me and Victoria's lab section, that doesn't necessarily mean that we are the ones that are going to be grading your lab reports. So because during the summer, all of the labs have varying numbers of students. We divide the number of students equally for grading in between all of the TAs. So you will get an email by the end of the week from the person who is going to be grading your lab reports. So if you have any questions on lab report writing, you can come to me and Victoria, but it would be better to go directly to the person who is grading your lab report. All right, so the long lab report. We will only be doing one of those. So the long lab report has all of the sections. So title page, abstract, intro, methods, data, discussion, conclusion, and a reference section. So, make sure to follow the lab report writing guide for this one. So real quick, let's talk about how much time you should be spending on the long lab report. So if you completed all of the data and all of the data in your lab notebook, or if you are following along on your computer and you're doing it on your computer already, that might be preferred because that will save you some time. But the actual writing part should not take more than 5 to 6 hours. If it is, come to me or Victoria for any writing tips, because we don't want you spending tons of time on your lab reports. So the abbreviated lab reports should only take 3 hours or less. So if you're spending more than 3 hours trying to write your lab report, that's too much time and we will need to help you. We do know that when you are doing the introduction section, that does take a little bit more time because you will need to get, sorry. You will need to find 2 sources of information to support the theory that you're writing about in the introduction. So that does take a little bit more time. In addition, when you have sources, you also need to cite those, which also takes a little bit more time. So we do recognize that, but still it should be less than 3 hours that you're spending. Okay. So for all of the abbreviated lab reports, you always need to have a data section. So the data section is going to be the same across all lab reports. What can differ is the abstract, introduction, methods, conclusion, things like that. If there are discussion questions at the end of the lab manual pages, you need to include the answers to those questions in your lab report. So not all of the labs have discussion questions, so make sure you note those. Okay, worksheets. So for the worksheet labs, again, you can type the worksheets up, but a lot of the worksheets in this lab have pre-formatted tables that you would have to recreate in Word or Excel. And if you would like to do that, go ahead. But it might be quicker to just print out the page and handwrite, but that's up to you. All right, okay. So you will get a grade for your lab notebook at the end of the semester. So what that means is you will submit your lab notebook. So that includes all the pre-lab stuff, your data, calculations, observations, and your lab summaries. So this is why you want to keep everything in one place, even if it is on the computer, because you will need to show that you have a dedicated lab notebook at the end of the semester and that you were working in it. Okay. Okay, so another thing about lab notebooks, why are they important? So when you are part of a research group, whether it is in academia or in industry, your lab notebook is intellectual property of that research group. And so your work, as well as the dates of what you worked on, is intellectual property. So it's a legal document that can be used to prove that your research group made a discovery. So for instance, when they discovered CRISPR, there was like this giant legal battle between two research groups as to who discovered CRISPR first. And so what the intellectual property lawyers do is that they actually go look at the scientists' lab notebooks in the dates and the signatures to see who did it first. So as scientists get used to keeping a lab notebook and make sure that you are recording everything in it and you have dates, okay? So obviously for general chemistry, that's not intellectual property, but just get used to the practice. Okay, so what happens if you miss a lab? So if you are going to miss Victoria's lab on a Monday, you need to let her know. And your only option would be to attend a Tuesday lab section instead. So Mondays and Tuesdays teach the same lab. Wednesdays and Thursdays teach the same lab. So if you're gonna miss a Wednesday lab, you have to let me know, and we will see about getting you into a Thursday lab. So if you miss a lab and are not able to make the following day's lab, you can use that as your one absence for the semester. But after that, we won't be able to make additional accommodations in the same way. Okay, so again, if you can't make it to another lab, we will give you the data for the lab so that you can write the lab report for that lab, but you will not get any of the lab conduct grade for that day. So the lab conduct grade is out of 5, I think, right, Victoria?
It's out of 10.
10, okay. So essentially, basically, you'll lose 10 points out of the total amount of points that you can earn for the lab. So that's what you're gonna miss out on if you can't make the lab, but we will give you the data so that you can do the lab report, and you will have to watch the lab video on your own time. All right, so if you have a disability, which many people do, you need to, you don't need to, but you may disclose your disability with the Ross Center. And the Ross Center is in charge of working with people with disabilities to notify professors about any accommodations that you may need. So there are plenty of accommodations that we have here at UMass Boston. So whether you are needing extra time on writing, exams, quizzes, things like that, they can inform us that you might need some extra time. For instance, if you are a wheelchair user, in the labs, we have lab hoods that are lower to the ground so that people in wheelchairs are able to work in the hood, things like that. Obviously, we're not in the lab, so the last one I mentioned is a non-issue this semester, but in the future, if that's something you might need, the Ross Center can help with that. So if you have, if you are signed up with the Ross Center, make sure that either you tell us what accommodations you need, and make sure that the Ross Center emails us. So as TAs, because we are not professors, we don't always get notified by the Ross Center, especially in the summer. So if you are with the Ross Center, please double check with them to see if they have emailed us your accommodations. So for instance, so far, anybody in this lab, if you have accommodations with the Ross Center, they have not emailed me yet. So please make sure that you do that. Okay, the last thing that we're going to talk about for the intro is not the most exciting, but cheating and plagiarism. So we use SafeAssign, I believe, for our plagiarism software. So if when you submit your lab report to us through Blackboard, it does check your lab report against everything that has ever been submitted to SafeAssign in general. So not just from this university, but every university, as well as documents online and online resources. So if you paraphrase somebody else's work, if you paraphrase your own work, if you copy word for word, we will find it and we will know about it. And unfortunately, if you do this, the first time you will have to rewrite your lab. The second time, it's just going to be a 0. So if you are paraphrasing something online, just cite it as a source. So if you are getting something particularly off Wikipedia, Wikipedia cites their sources. So if you're looking up, you know, some kind of reaction on Wikipedia and it says blah, 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 look at what their source is and cite that source. Never cite Wikipedia, never cite Chem LibreTexts. They do their citing for you. So just look at what source they're using and use that source. I mean, I don't know about Victoria, but that's what I do in my own writing. Okay, so yeah, if you are getting something offline, just cite it as a source. And then it's not plagiarism. So don't cheat. We know that people who plagiarize, it's usually out of desperation, and it's not because you're a bad student. But if you are feeling like you need to plagiarize in order to submit something, we would rather have you come to us for help than plagiarize, because that's gonna be so much of a bigger issue. Okay, so we're here to help you guys. All right, so intro is over. Does anybody have any questions about what we went over in the intro? I know it's a lot.
So I have a question, but it's not necessarily what you went over.
Yeah, go ahead.
For today's lab, were we supposed to submit the pre-lab?
You were, but because it's the first day, I left the submission open until midnight so that you guys can submit things. And I also know that there was some confusion with the voice threads. So I left that, so that's why I left it open extra late today.
And also, can you guys change the date of when things are due on Blackboard?
You mean in general?
Yeah, because some stuff says like February of 2021.
Oh, yeah. So we'll be doing that as the semester goes on. Okay, so Chris, go ahead.
Oh, I just have a question about that. What is the best way to communicate with the two of you? Because Blackboard says don't send emails, and then I'm just curious what you prefer.
Email.
Okay.
So good. I didn't know that Blackboard says not to email us. That's really weird, because like that's the only way you can contact us. All right, so send us emails. So we may only respond within business hours. I know I'm terrible with boundaries, so I will email every time I see something. So yeah, just email us. And then that, good question, because that's something else I wanted to talk to you guys about. So at the end, we will be ending lab at 3:30. So we will be doing lab for 3 hours. And then Victoria and I will each have 1 office hour a week on a different day. So my office hour will need to be between Thursday and Friday, obviously, because your lab report for me is due on Saturday. If you guys could respond in the chat whether you would like to have it. So I also teach labs on Thursdays. No, Tuesday? Yeah, okay. So I am free on Thursdays and Fridays. Would you guys prefer a Thursday office hour or a Friday office hour? If you could just respond in the chat, everyone.
Can I ask you another question while everyone's doing that?
Yeah, go ahead.
How do you keep a notebook? Just out of curiosity, because I'm considering doing everything on the computer rather than like the old school way.
Okay, so if you are doing everything on the computer, I would just keep a folder on your computer of everything.
Okay.
Yeah, that would be the easiest way if you're doing it on the computer.
All right, thank you.
Yep. So Chris, that can be a combination of any types of documents. So like in that folder, if you have certain things that are Word documents, certain things that are like Excel documents, certain things that are scanned in, as long as it's all in one place, that's going to be the easiest for you. So for instance, when I'm teaching, like I have everything, I have a TA folder, and then I have things broken down by the courses and then by semester for me. So something similar for you, that might be good. Like if you guys are, yeah, if you're doing most everything on your computer, I would, whatever hierarchy system works for you, I would just keep it consistent through like all of your courses. I think that would be easiest. So it looks like all but one has said Thursday. So, so I'm sorry, Williams, but I will hold my office hours on Thursday. So I will hold office hours. I will think about a time, but it will be on Thursday. And then Victoria, do you know when you want to hold your office hour?
So I usually just do mine by appointment.
Okay.
So just email me a time if you want to come to my office hours, and then we can figure out what works for both of us.
Okay. That sounds good. Yeah, so I will have a dedicated office hour on Thursday. I'll think about a time and send everybody an email and also post it on Blackboard. Otherwise, so the Microsoft, good question. So the Microsoft and Excel assignment is due 1 week from today. Same thing with the safety quiz. So you have 1 week to do those. So the Microsoft and Excel assignment is the exact same as Chem 117, if you took that with us. So just letting you know. Okay, so let's get into today's lab.
Sorry, one last question about the pre-lab.
Yep, go ahead.
I don't know if you're anal about this, and sorry for the word if it offends anyone, but like, what are you looking for in key concepts? Like, are you looking for, like, you know, we're using calculations, or is there something? Because I know my last TA for Chem 115 was like really anal about it. So I was just wondering what your thing is.
No, so like, as long, basically, the purpose of the pre-lab, in my opinion, is to make sure that you are prepared for lab. So if what you have written shows to me that you've put some effort into it and are prepared for the experiment, it's fine. If you write a bunch of garbage or like nothing, then you're not going to get a lot of points. So it doesn't have to be perfect, you know, but it does need to show you put in effort. Does that make sense? Does that help?
Yes, thank you.
Okay, great. All right, so let's get into stoichiometry and the limiting reagent. So, all right. So the main objectives of today's experiment is to determine the identities and quantities of limiting and excess reagents for a given chemical reaction. So what they mean by identity is when you are reacting 2 or more chemicals, which one is the limiting reagent and by how much. So the quantity would be how much product can you make from the limiting reagent, and then whatever the excess reagent is, how much leftover of those excess reagents are you going to have? So that's what that sentence means. So in order to do this, we need to determine what the theoretical yield is based on the amounts of reagents that we're starting with. The next thing to do is determine what the actual yield is. So the theoretical yield is theoretical. The actual yield is experimental. So this means what we actually produced in the reaction. And so based on the theoretical yield, so how much we could have made versus the actual yield, how much we did make, we can figure out what the percent yield is. So the percent yield is the actual amount divided by the theoretical amount. So essentially, what percent of the theoretical amount did we actually make? Okay, so let's review what stoichiometry is. So in this example, we have the reaction to make water from hydrogen gas and oxygen gas. And let's take a look at the ball and stick figure that we have here, or just the ball figure. So if we count the number of atoms in each, so water, let's start with the product. Water has 1 atom of oxygen and 2 atoms of hydrogen. The oxygen molecule has 2 atoms of oxygen. And for hydrogen, there are also 2 atoms of hydrogen in each. But water has 1 oxygen and 2 hydrogens. So that means we need twice as much hydrogen as we need oxygen. So the first thing we need to do in stoichiometry is make sure that our chemical equation is balanced. And we do this by adding coefficients to the beginning or in front of the different reagents as we need to. So we can't change the compound itself. For instance, instead of saying H2 gas and O2 to make H2O, we couldn't just say H2 and then O regular, because just O is a completely different compound than O2. So we can't break up these molecules, but we can add more of one than the other in order to balance the amount of atoms. So when we are balancing the chemical equation, we want to make sure that the number of atoms on one side of the equation is the same as the number of atoms on the other side of the equation. So on this side of the equation, we have O2, so we have 2 oxygen atoms. And over here we have water, which is H2O. So in just H2O, there's only 1 oxygen atom. So in order to go from 1 oxygen atom to 2 oxygen atoms, the only way we can do that is by adding a 2 in front of H2O. So in order to have 2 oxygen atoms on this side of the equation, we have to have 2 molecules of water to do that. But now we have 4 atoms of hydrogen. So 2 times 2 is 4. So now we have to go back to the hydrogen and balance it over here by adding a 2 here. So now we have 4 hydrogen atoms on this side and 4 on this side. So that is the very first step to starting our calculations. So we always want to make sure that our chemical equation is balanced before we start. Okay, so in the another thing we need to do is to make sure that the amounts we're using are consistent. So for instance, in this example, they're saying 4 grams of H2 plus 32 grams of O2 makes 36 grams of H2O. Now, in order to make sure this is correct, obviously we would have to, or it's not obviously, but we would have to convert these amounts to moles to make sure that that's possible. But I do want to point out that that based on the law of conservation of mass, that 4 grams plus 32 grams does equal 36. So very quickly, I just want to point out that if your product amount in grams is more than the sum of your reactants, then something else is going wrong, because you cannot create matter. So the amount of products always has to be equal to the sum of the reagents, or if it is your experimental amount, it has to be the same or less. If you have a higher mass experimentally, that means you have contaminants in your product, but we will get to that at a different time. Okay, so let's go back to the balancing here. So what this means, the 2 H2 and 1 O2 makes 2 H2Os. We can also think of this as moles. So 2 moles of H2 gas plus 1 mole of O2 gas makes 2 moles of H2O. And so when we talk about the molar equivalencies of things, that's what we're talking about. We're talking about the balanced equation. So this would be the stoichiometric equivalency. So we would say the stoichiometric equivalency here is 2 to 1 to 2. So when we say things like what's the mole ratio, things like that, that's what we're talking about, is the balanced chemical equation. Okay, so when we are doing stoichiometry, you always want to convert everything into moles, always. So you cannot compare the grams of one thing to the grams of another thing, because one molecule has a different amount of grams per mole based on its molar mass than another compound. So you can't compare the mass of one compound to the mass of another compound and talk about quantity in moles, okay? So if we start with grams of a substance, in order to compare that to another substance, we need to convert it to moles. So we can do that by using the molar mass. So the molar mass is the grams of a compound in 1 mole of that compound. Okay, so we can convert grams of one substance using molar mass to the amount of moles we have of that substance. And we can do the same thing with another substance. And so in that way, we can compare the amount of moles of one thing to the amount of moles of another thing. Okay, so how will we do this? Here's an example of the combustion of sugar with oxygen. So if we have 1 gram of sugar, C6H12O6, how many grams of H2O are produced? Okay, so we can't directly relate grams of one thing to grams of another thing. So we need to first convert what we know into moles. So grams of H2O is a big question mark. So that's what we're trying to find. But we do have the grams of sugar. So we are starting with 1 gram of sugar. So the first thing we need to do is convert that into moles. So how many moles of sugar are in 1 gram of sugar? Well, we know that for every 1 mole of sugar, there are 180 grams of sugar. So 180 grams of sugar equals 1 mole. So if we multiply 1 gram of sugar by the inverse of the molar mass, so 1 mole over 180 grams of sugar, we have now converted it into moles. So 1 gram of sugar equals 5.56 times 10 to the minus 3 moles of sugar. So it's 10 to the minus 3. And this makes sense because 1 gram is way less than 180 grams. So our amount of moles should be way less than 1 mole. Okay. So now we need to figure out how much water we can make. And in order to do that, we need to know what the molar ratio is of our reactants to our products. So for every 1 mole of sugar that we have, we can make 6 moles of H2O. So the next thing we need to do is multiply our moles of sugar that we just found. So our 5.56 times 10 to the minus 3rd moles of sugar, that's how much we're starting with. And we're going to multiply that by 6 moles of water over 1 mole of sugar. So our units, moles of sugar, will cancel out here. And what we're left with is 6 times 5.56 times 10 to the minus 3rd moles of H2O. So 6 times our moles of sugar equals 3.33 times 10 to the minus 2 moles of H2O. And it makes sense that this number, this moles of H2O, should be bigger than our moles of sugar because we're multiplying it by 6. So we're starting in our chemical equation, 1 mole of sugar makes 6 of H2O. So our H2O moles should be bigger than our sugar moles. Okay, but we can't stop at moles because our question says find how many grams of H2O are produced. So we need to convert moles back to grams. So in order to do this, we want the mole units to cancel and we want to be left with grams. So we are going to multiply by the molar mass of water. So this is the opposite of what we did for sugar. So to go from grams to moles, we want to use the inverse of molar mass, in which you have moles over grams. When we're going from moles to grams, we want to make sure that we are using the regular molar mass with grams over moles. So we are going to multiply the number of moles we can make by the molar mass of water, and we get 0.6 grams of H2O. So we are starting with 1 gram of sugar, and 1 gram of sugar can make 0.6 grams of H2O. Does anybody have any questions on this process of calculations? Okay. So in every reaction, the amount of product formed is determined by the amount of reactants. And so in the reaction, based on the number of moles of our reactants, we can figure out which one is going to be the limiting reactant and which one is going to be the excess reactant. So we need to figure out first how many number of moles of a reactant we have, and how much product we can theoretically make from each reactant. So the reactant that is less, or the reactant that can make less product, is the limiting reactant. And that reactant is going to be completely used up in the reaction. So at the end of the reaction, we are going to have 0 amount of the limiting reactant left. However, the other reactant will have excess left over, which is why it's called the excess reactant. All right. Okay, so here we have another example. So let's take a look at our chemical equation. Again, we're using the formation of water from hydrogen and oxygen. So remember that it takes twice as much hydrogen as it does oxygen to make H2O. So in this example, they're giving us the, we're starting with moles this time instead of grams. So they're saying that we're starting with 10 moles of H2 and 7 moles of O2. And they're asking, what is the limiting reagent? How much H2O can be formed? And how much excess reagent is left over? So the first thing that we need to do is find out how much product we can make from each of these starting amounts. So let's start with, so in this example, they're starting with oxygen. So if we start with 7 moles of oxygen, sorry, I hate how they do this. So hold on. We are, oh, I don't have a whiteboard. Never mind. Okay. Oh, yes, I do. Okay, so we are starting with 7 moles of O2. Okay. We're starting with 7 moles of O2. So in our chemical reagent, hold on. So, yeah, I'm gonna share my screen. Okay. Now the whiteboard's gone. Sorry, guys, hold on. Okay. So in our chemical equation, we can make, so for every 1 mole of O2, we can make 2 moles of H2O. Okay, so this is based on our chemical equation that 2 H2s plus O2 equals 2 H2Os. Okay. So based on the molar equivalence, for every 1 mole of O2, we can make 2 moles of H2O. So now we multiply the top numbers and divide by the bottom number. So we can make 14 moles of H2O, using 7 moles of O2. Okay. And then for our other reactant, it says we have 10 moles of H2O. H2. So how much H2O can we make with 10 moles of H2? So based on our balanced chemical equation, for every 2 moles of H2, we can make 2 moles of H2O. So you might see that these numbers cancel out, right? So 2 over 2 equals 1. So our 10 moles of H2 can make 10 moles of H2O. So now let's look at which number is smaller. So this number here, 10, is smaller than 14. So that means our limiting reagent is the 10 moles of H2. So now let's figure out how much of the excess reagent we have. So our excess reagent is the O2, okay? So in order to do that, we can figure out how much O2 is left over by figuring out how much O2 has been used up. So let's do this again. So we need to figure out how much O2 is used up based on how much H2 we start with. So we are starting with 10 moles of H2. Okay, and based on our equation, for every 2 moles of H2, we use 1 mole of O2, right? Based on this ratio. So 10 divided by 2 equals 5 moles of O2. So we have used 5 moles of O2 so 10 moles of H2 will need to react with 5 moles of O2 in order to make 10 moles of H2O. But we started with 7 moles of O2. So how much oxygen is left over after the reaction? So we started with 7 moles of O2 minus how much we used, 5 moles of O2. And that means we have 2 moles of O2 left over. So the 10 moles of hydrogen gas, H2, is our limiting reagent. Our oxygen is our excess reagent. And our 10 moles of H2O is our theoretical yield. So theoretically, using 10 moles of H2 and 7 moles of O2, we can theoretically only make 10 moles of H2O, and we will have 2 moles of O2 left over. So this is our theoretical yield. Now, in lab, we can do this experiment of reacting H2 and O2 and measure how much H2O we actually make, and that would be the actual yield. So say, for instance, we made, theoretically or experimentally, we made 9 moles of H2O. So our percent yield would be the actual amount divided by the theoretical times 100%. So our percent yield for that reaction would be 9 moles divided by, so the 9 would be our experimental yield if we experimented and got 9 moles, divided by 10 moles, which is our theoretical yield. And then we multiply that by 100%. So 9 divided by 10 times 100 would equal 90%. So our yield in this example would be a 90% yield for this reaction. Okay, so does anybody have any questions on this example, or how to calculate theoretical yields and the limiting and excess reagents? Does anybody have any questions?
I have a question, but it's not really about this. I just thought of it.
Yeah, go ahead.
So I heard Victoria saying that we have to turn in our lab like after, so like at 4:40. That doesn't mean, does that mean the abbreviated lab report, or is it just like data?
She was mentioning the lab summary at the end of lab.
Oh, okay, thank you.
Yep. Okay, so does anybody have any questions on the stoichiometry here?
Oh, I have a question.
Yeah, go ahead.
Oh, where is the theoretical yield going to be given to us? Because I just remember when we were in actual lab, there was like a book we looked through to find that. Or are you just going to give it to us?
No, so you will have to calculate it.
I thought we calculated. Oh, okay. I understand.
Yep. So, okay, so we will get to that. Don't worry. All right, so let's go back to the slideshow. No, this one. All right. Okay, so let's get into.
Sorry,
Yeah.
I have one question before you continue. Are you
Yep.
going to be posting this recording on our Blackboard?
Yes.
Okay, perfect.
Okay, so let's talk about today's actual experiment and what we are going to be doing. So we are going to be using 2 table salts and we are going to mix them to form an insoluble product. So calcium chloride in this reaction equation, it says it's aqueous. That's what that AQ stands for. So what that means is both of our table salts, calcium chloride and sodium carbonate, are going to be dissolved into water separately. And when we mix those solutions of those 2 different salts together, we are going to form, it's going to be a precipitation reaction in which the calcium from calcium chloride is going to react with the carbonate of sodium carbonate to create calcium carbonate solid. So our product is calcium carbonate and our reactants are calcium chloride and sodium carbonate. So the other product that we are not concerned with in this reaction is NaCl. So NaCl is going to remain in solution. That's why it says aqueous. So we're not going to have sodium chloride, really. We are going to be having sodium ions and chloride ions in solution. But the white product precipitate that you see will be calcium carbonate solid. Okay, so there are 4 trials in this reaction. And the 4 different trials are going to be using different volumes of the 2 solutions. So we are going to vary the amount of starting material to see how much product is made. So we can calculate based on how much we start with what the theoretical yield will be. So that's the first step. Before you start your reaction, you will always want to calculate how much product you're expecting to make. So you know what you're expecting. And then at the end, after the solid calcium carbonate is filtered and dried, you will measure it, or it will be measured in the video to see how much was actually made. So at the end of the experiment, you'll get the actual yield. And before you start the experiment, you should have your theoretical yield. And then based on the different amounts of the starting materials, you will be able to determine which should be the limiting reagent and which should be the excess reagent in each trial. So each trial could be different. So sometimes it could be calcium chloride, and sometimes it could be sodium carbonate, depending on how much we're starting with. Okay, one thing I want to point out before we move forward is that between calcium chloride, sodium carbonate, and calcium carbonate, it's all a 1-to-1 stoichiometric ratio. So in this reaction, we don't have to worry about the stoichiometric ratio of our reactants. Okay, so the first thing that's going to happen is the reaction mixtures will be dispensed. So in these trials, these are the amounts in volume that we're starting with. So in trial 1, we're starting with 25 milliliters of calcium chloride, 25 milliliters of sodium carbonate, and so on and so forth. So in your tables, I would recommend that if you have not done so, that you write these numbers down. So these numbers should also be in your lab manual, and we will see them again in the video. So in class, we would have burettes of the materials, and we would dispense them accurately with the burettes into 4 different beakers. So when you're doing different trials at the same time, you would want to label all of your beakers corresponding to which trial they are. So for instance, we would have beakers 1, 2, 3, and 4 corresponding to the different trial numbers. We will mix the reaction beakers with stirring rods. Okay. So when you are filling a burette with stuff, so for those of you who are biologists, you might make your own columns, purification columns in biochemistry. So this is going to be important for you. So the first thing that you want to do is make sure the burette is clean. And so we first do this by rinsing the burette with water, DI water, always DI water. And then you always want to rinse the burette with the chemical you're using. So for instance, if we have 1 burette with calcium chloride, we want to do a rinse with a few milliliters of calcium chloride. So that will ensure that there's no excess water, because if there's excess water in the burette, the concentration is going to be off. So you always want to rinse whatever you're measuring a solution with the solution before you dispense. So we would rinse our burettes respectively with the calcium chloride and the sodium carbonate solutions. When you fill the burette, you want to make sure that there are no air bubbles, that it's not dripping. If it's dripping, that means the connection's just not tight enough, things like that. You always want to record the starting volume before you start. So most of the time in burettes, the numbers go up as the burette goes down. So you always want to record the number you're starting on. So you don't always have to start when you're using a burette. You don't always have to start at 0. You can start at any number and end at whatever number is the amount. So say you need 25 milliliters. If you start at milliliter line number 3, you dispense 25 milliliters, and that 25 milliliter mark, because you started at 3, will be at 28. So 28 minus 3 equals 25. Hopefully that makes sense. Okay, and then when you're mixing the solutions, you want to mix it with a stirring rod. And when you go in between each beaker, you will need to rinse off the stirring rod to make sure you're not bringing chemicals from one reaction to the next. Okay. Filtering. So filtering is one of the most commonly used separation techniques in chemistry, I would say in organic chemistry. So we always use some kind of funnel. So in this case, a Buchner funnel will have, it's funnel shaped. It has little holes on it. And what we do is we cover it with filter paper so that the anything that's liquid can be pulled through and whatever solid stays on the filter paper. So you put the filter paper on, it's connected to a vacuum. So it pulls the air through and all the liquid. So you turn the vacuum on and then you pour the solution with the solid in it over the Buchner funnel, and it will pull everything through except for the solid. And this will help take out all of the liquid, but the filtering process also helps dry the product. Okay, so we'll see that in the video, hopefully. Okay, so when we are filtering, we want to make sure that we want to pre-weigh whatever we are measuring our product on. So in this slide, it says the filter paper. This is not recommended. Usually, you would transfer the solid that's on the filter paper to a different vessel. So in this case, because we are drying our product under a heat lamp, we are transferring our product to a watch glass. So in this case, before you transfer your product from the filter paper to the watch glass, we want to measure we want to weigh the watch glass first. So you would weigh your watch glass, put the product on, and then weigh it. And you are going to get a crude amount. And it's crude because it's not fully dry yet. So once we dry it under the heat lamp for a certain amount of time, you reweigh it and it should be less. And what that means is that any extra water that was in your product has evaporated. So we'll do that once, and then you put it back under the heat lamp again for a certain amount of time, and then you reweigh it. And if the weights of the second and third weighings, so after evaporation, once they are about the same, that means there's no more water that is needing to be evaporated. Okay, and then the last thing to do is to make sure we clean up all of our materials. So here are some notes on drying and weighing the product. So in lab, we would have about 4 watch glasses per heat lamp. This is what the heat lamp looks like. We would heat for about 5 minutes, let it cool. And cooling really doesn't affect the weight. It's just if you try to pick up a really hot watch glass, you're probably going to drop it, and then there goes your product. So we always want to make sure things cool before we handle them. When you're transferring from the filter paper to a watch glass, make sure that one, your watch glass is big enough so that all of the product fits on the watch glass, and make sure nothing falls out of the filter paper onto like the lab bench or something. You want to make sure that when your things are drying, that you're keeping an eye on it. So obviously you don't have to like stare at it the whole time, but you just want to make sure that the filter paper is not burning, because as soon as you notice that the filter paper is turning color or it's burning, then you're immediately losing mass, because now there's a combustion reaction happening between the oxygen in the air and the filter paper. So that's a whole nother set of issues. And then you always want to make sure your products are labeled. So what does that mean? So the vessel that your product is on, you want to make sure you label it. So for instance, in this reaction, you had 4 different watch glasses, 1 for each trial. You would want to label it trial 1, 2, 3, and 4, just like we did for the beakers. Okay. So your data and calculations, this is what the table looks like in your lab manual. Make sure that everything is filled out. So the concentration of calcium chloride and sodium carbonate, you will need those concentrations to figure out how many moles of each that you have. So in the previous examples, we had grams, and we used molar mass to convert to moles. Now, in our experiment, we don't have grams, and we're not using molar mass. We have concentrations. So M molar stands for moles per liter. So instead of molar mass, we're using concentrations. And instead of grams, we're using milliliters. So we need to convert all of our starting milliliters to moles. So if we take a look at these first 2 sections, the one titled CaCl2 and Na2CO3, we need to convert the volume delivered, so the bottom lines of these guys, using the concentration to the theoretical yield in moles, okay? So you will need to figure out what the moles are for each trial for calcium chloride and sodium carbonate, compare them to each other, and figure out which one is less, or the limiting reagent. And the lesser amount of moles is going to be the theoretical yield of moles, okay? So if you have less calcium chloride, that's going to be the limiting reagent. If you have less sodium carbonate, that's going to be the limiting reagent. So Elijah, go ahead.
How do we convert from milliliters to moles?
Good question. So let's do an example using the first amounts. Sorry, I have a lot of things. All right, 25 and 25. Okay. Okay, so let me share the whiteboard again. All right, so, all right. So so the calcium, no, what is it? Yeah, calcium chloride. The concentration of calcium chloride that we're using is 0.050 molar, or moles per liter. For calcium carbonate, the concentration we're using is 0.1 moles per liter, okay? Those are our starting concentrations. So let's go through the math of trial 1 together. So we are starting with 25 milliliters of calcium chloride. Okay. So when you are doing stoichiometry, you always want to start with what you know, okay? So we know that we are starting with 25 mils of calcium chloride. We also know that the solution of this 25 milliliters is 0.05 moles per liter. So we need to go from milliliters to moles. Let's take a look at the units here. So the units of the concentration is in moles per liter, but we're starting with milliliters. So we first have to convert milliliters to liters. So the relationship between milliliters and liters is that for every 1 liter of anything, there are 1,000 milliliters. So that is going to be the first relationship that we need to figure out. Okay. So that will give us liters of calcium chloride. But now we need moles. So what we are going to do is, for the relationship between milliliters of something and moles of something is the concentration. So for every 0.05 moles of calcium chloride in this solution, there is 1 liter of calcium chloride. Okay, so let's cancel some things out here. So our milliliters are going to cancel out. Our liters are going to cancel out. And the unit we're left with is moles. So now we need to multiply the top and divide it by the bottom. So 25 times 0.05 divided by 1,000. That is going to be equal to 0.00125 moles, I believe. Let me double check that.
Yeah, that's what I got too.
Okay, great. So that's how many moles of calcium chloride. Okay, so we are also starting with 25 mils of Na2CO3. So now we have to figure out how much moles that is going to be. So we're going to do the exact same thing. So the first step is converting to milliliters. So for every 1 liter, there is 1,000 milliliters. But our concentration is different this time. So be careful about that in your Na2CO3 calculations. So our concentration for Na2CO3 is 0.1 moles of Na2CO3 in every 1 liter, right? So now the calculation is going to be a little bit different. So again, let's cancel out our units. So now we have 25 times 0.1 divided by 1,000. So that is gonna be 25 divided by 1000 times 0.1. That is going to be 0.0025 moles of Na2CO3. All right, so because in the chemical equation that we saw before, these guys are in a 1-to-1 molar ratio with each other. The concentration is, so Alejandra, no, the concentration is not different for every trial. So you're starting with the same concentrations of everything. The only thing that's different is going to be the volumes. So again, the other thing I want to point out is that this is based on 25 milliliters. But when we watch the video, the actual amount dispensed is going to be, it's going to vary a little bit, but it's going to be pretty close to 25 milliliters, okay? So this is going to be an example of that first thing, the first trial. Elijah, go ahead.
So how do we know that we're starting out with 0.05 moles of calcium chloride and 0.1 moles of
So in the lab, the solutions that you're using would be labeled with the concentrations that they have. So when we watch the video, the person who made the video will have to tell you what the concentrations are.
Okay, so it's something we're given, right?
Yes, yes, yes. This is given to you.
Okay, thank you.
Yes. So when we watch the video, these amounts will be measured. So you want to, in your data, you want to use the measured amount, okay? But this is just an example of the first trial. So it'll be close to 25 milliliters when we watch the video, but it might not be exact. Anyway, but we can still see the relationship here. So let's take a look at the amount of moles that are that we have here. So if we start with 25 milliliters of 0.05 moles of calcium chloride, we can only have 0.00125 moles of calcium chloride. So if we start with the same volume of sodium carbonate, but sodium carbonate's concentration is higher, we are starting with more moles of sodium carbonate. So the limiting reagent in this case, so the limiting reagent is the one that is smaller. So the smaller number here is calcium chloride. So for trial number 1, we are using this amount of calcium chloride. And so we're going to have excess Na2CO3. So in the first one, calcium chloride is our limiting reagent, and sodium carbonate is our excess reagent. Right, okay, so the moles of the limiting reagent will be used to calculate the theoretical yield. So our overall chemical equation, right, is calcium chloride plus sodium carbonate makes calcium carbonate. I'm leaving out the sodium chloride because they're spectator ions and we don't need them. So this is our balanced chemical equation. So everything is a 1-to-1 ratio. So now that we have the limiting reagent of calcium chloride, we can figure out theoretically how much calcium carbonate we have. Okay, so let's do that. So now we can start with this molar amount of calcium chloride. So 0.00125 moles of calcium chloride is what we have. We need to figure out how much calcium carbonate that makes. So now we need to use the relationship of the chemical equation. So for every 1 mole of calcium chloride that we have, we can make 1 mole of calcium carbonate, okay? And so we want the moles of calcium chloride on the bottom because we want to cancel out those units. And we want to be left with moles of calcium carbonate at the end or after this relationship, okay? But your lab report is asking for the theoretical amount in grams. So now we need to go from, well, actually, let's figure out what these moles are first. Oops. Okay, so let's figure out what these moles are. So how many moles of calcium carbonate did we make? So because this is a 1-to-1 ratio, we made the same amount of moles. So 0.00125 moles of calcium chloride makes 0.00125 moles of calcium carbonate. So now we need to convert that into grams. So we are going to do that using the molar mass, okay? So for every 1 mole of CaCO3, let's just Google that molar mass real quick. Molar mass of CaCO3. Okay, 100.09. So for every 1 mole of calcium carbonate, there's 100.09 grams of calcium carbonate. And again, we're using this relationship in its regular form because we want to cancel out the moles here, okay? And we want to be left with grams. So the total amount of grams we can make, we just need to multiply the amount of moles by the molar mass. So 0.00125 times 100.09. That gives us 0.125 grams of calcium chloride. I mean, calcium carbonate. Okay. Now let's talk about significant figures. So depending on how many sig figs we go through on the milliliters will determine how much we get here. So when we watch the video, we'll see what Nathan gives us, but if he goes to 1 decimal point, we can get 3 sig figs. If he goes to 2 decimal points after the milliliters, we can extend this amount out to 4 significant figures, okay? All right, so does anybody have any questions? Okay, so that is how we are going to be doing all of the calculations. So the only thing that's going to be different in the calculations is the amounts that you start with of each thing. So your limiting reagent is, in this case, because our chemical equation is a 1-to-1-to-1 ratio, the limiting reagent is always going to be the lower number of moles, okay? And the excess is always going to be the bigger number. So the smaller number is what we're looking for here, okay? All right, so let's see. All right, so let's finish up the PowerPoint real quick. Okay, so the lab report, we have a short lab report for this lab. You will be writing a conclusion, a discussion, and a data section, not in this order. So you should have your data section first. So all of the tables need to be properly filled out. And we should have examples of your calculations that you've done. So you don't need to show all of the calculations that you did, but for each different data point that you need for your table, we should see an example of that calculation. So for instance, if you want to just show all the calculations for trial 1, that would be good. So that would be in your data section. The next thing you need to write is the discussion section. So you need to discuss what happened and what the results are for the lab. So I would recommend going trial by trial. So you can say for trial 1, the limiting reagent was such and such, and we got such and such % yield, and do that for each trial. And then in the conclusion section, this is where you're going to summarize the experiment, okay? So if you go to the lab report writing guide on Blackboard, it will have much more details for you. Okay, so that is it for the slideshow. Let's move on to the video. All right.
Professor,
Yep.
before we get into it, just for my stress level here, I should be able to just watch this video, fill out the tables accordingly, and then in my free time, I can do all the calculations and write. I'm not supposed to be doing that like during this class, right?
That's up to you, how
Okay.
you want to use your time.
All right, and then my other question is, would you be willing to post the PowerPoints in like, so that we don't have to watch the voice threads?
Yes.
That would be great.
Okay. Yep.
Thank you.
All right, so let's watch the video. I do have it somewhere. All right. Okay, so my volume settings are as high as they can go on my computer and on YouTube. So if you can't exactly hear what Nathan is saying, I think it's going to be okay. What you basically just want to watch what he's doing, and then I will pause when he does a recording so that you can record that number. All right.
Welcome to the Chem 118 Limiting Reagent Lab. The tools for today's lab are going to be 4 beakers, watch glasses, filter paper, vacuum filtration setup, and a burette, as 2 Erlenmeyer flasks for collecting the reagents needed. And there will also be beakers needed for waste collection. These solutions used as reagents will be located in the fume hoods in giant carboys with their names and concentrations written on each.
So these are the concentrations. Oh, sorry, let me full screen this. Okay, so our calcium chloride is 0.05 molar and our sodium carbonate is 0.1 molar. So in the concentration of your, on your table, you can write those numbers. So 0.05 molar in all of the trials for calcium chloride. And then for all of the trials for sodium carbonate, you can write 0.1 molar. And just, yeah, okay.
With names and concentrations written on each. The beakers that you use for the reactions need to be labeled 1, 2, 3, and 4. Make sure they are clearly labeled, and if there are multiple labels on each of the beakers, just try to remove as many of them as you can, and if you are having trouble, go ahead and place a new sticker on top of the previous one to save room. Also do the same for the watch glasses. Take the lid of the glass cover to match your carboy. Open the tube and then open the carboy and empty approximately 100 milliliters into your flask. Then close the tap on the carboy and then close the fume lid.
Your burette, you want to make sure that it is in fact closed before you pour any liquid into it. Horizontal is closed, vertical is open. Always check this once again before pouring liquid in. So the next thing we're going to do is we're going to rinse our burette. This is our lovely burette setup. You want to make sure that the burette is closed before you pour any liquid in it. Seems pretty logical. Horizontal on the nozzle is closed, vertical is open, so we're going to close that completely. Then you're going to pour calcium chloride, just a little bit. Over your head. This gently and carefully. Liquid down the burette. Do this too quickly, or you will pour it on your gloves, which is not the goal. Just rotate it. Make sure all the sides are covered. Sides still in there. And then we are going to put it back on our burette holder and dump the waste liquid into our waste beaker. I'm going to reclose the burettes and add the rest of the calcium chloride. Okay. So, next two important factors are, one, we need to make sure that there are no air bubbles in our burette. Typically, you're going to find air bubbles in the tip. Sometimes you will get an air bubble stuck in the nozzle. So, first thing you're going to do is open up, let some liquid out. We're going to check for air bubbles. Alright. So if there are any air bubbles stuck in our burette, we're going to give it a nice little split while it's open. That will take care of those. And now we can go ahead and continue with our experiment. So before continuing our experiment, the first thing that we need to do is we need to note where the volume is on our burette. So it might be a little bit difficult to see, but there is a curvature to our liquid. The bottom of that curvature is the meniscus, and that is what we want to measure to. So you want to be at eye level with the meniscus, which if you're short like me, there is a step stool. Eye level with the meniscus, and you're going to measure to the 100th decimal place. So this looks to be about 14.10 approximately. And at the end of the day, you are having to visually determine this number. So there's always going to be a slight difference between your eyes and your lab partners. So when taking measurements, to be the most consistent, the same person should read the burette for each trial. So one lab partner can read for the first trial, the second lab partner for the second trial, so on and so forth. Okay. So make sure we don't have any drops.
So just to remind you guys, so the initial burette reading for this trial will be 14.10 milliliters for the calcium chloride. So remember, in this burette, there's the calcium chloride. So if you see, so Amy has made a copy of the table from your thing, and the concentration here for each trial, right? It's 0.05 molar. The initial burette reading, so the next line down for trial 1 will be 14.10. That is your first initial burette reading for trial 1.
Make sure we don't have any drops on our burettes. I'm going to put beaker 1 under our burette. I'm now going to dispense 25 milliliters, which this volume is found in table 1 of your lab manual. So as I'm starting at approximately 14, I'm going to dispense 25 milliliters, stopping around 39.10. Get close to your desired amount. You're going to slow the burette down to a drip so that you can get as accurate as possible. Reading the meniscus, we are right at 9 points. I am now going to open the burette and let the remaining liquid dispense into the waste beaker since we don't need it.
Okay, so the final burette reading for trial 1 for calcium chloride is 39.12, as Amy said. So the volume dispensed is going to be the final reading minus the initial reading. So the amount dispensed is what you are going to use to do your theoretical yield calculations.
At this point, you want to rinse out the burette with water. This is to ensure that there is going to be no contamination when you add the second stock solution to the burette. Make sure that you fill up the burette with clean deionized water. And after you do that and let it drain a little bit, you want to do what you did before and take the burette and twirl it around a little bit so that you can coat the entire inside. Rinse it out a few more times before moving forward as well. To do this is to prevent precipitation from happening within the burette itself. If this were to happen, it would mean that the burette was not properly cleaned, and you would need to restart the experiment after making sure that all of the precipitate was removed from the burette. Make sure that you rinse out the funnel as well, since there can be contamination from that.
I'm going to now add the sodium carbonate. Once again, we're going to check air bubbles. There were some in there. All right. We'll measure where our meniscus is. At 1.00. And 25 milliliters of carbonate as well. So I'm going to put our reaction beaker and dispense 25 milliliters. We are now going to 6 milliliters.
So
In the video, you can see the precipitate forming as the sodium carbonate solution is added to the calcium chloride. You carefully make sure that you do not overshoot the amount of liquid you're supposed to put into the beaker. Getting close to where you want to stop. Make sure that you close the stopcock a little bit so that the stream slows down. This makes it easier for you to stop at a specific point rather than just randomly stopping. Added the desired amount of solution to the beaker. You can read the meniscus on the burette and record the volume listed on there. Added each solution to the beakers. You can take the glass stirring rod and then stir the solutions. This is to ensure that there's a complete reaction and that all of the maximum precipitate possible is formed. This, make sure to rinse off the glass stirring rod with some DI water. This will not affect the amount of precipitate, but it will ensure that there is no precipitate transferred to the glass rod during the stirring process. Make sure to clean off the glass stirring rod before switching to a different solution. At this point, you're going to take...
So I just want to point out, you might be wondering if it's okay to rinse the stir rod with DI water right into the reaction. Yes, you can. So adding more water to the reaction now that we've added the reactants, it doesn't matter, because after the reaction is complete, we are going to be filtering out all the water anyway. So the water is not going to affect the solubility properties of the compound. But this also ensures that any precipitate that was on the glass stir rod remains in that beaker.
watch glass and the filter paper you are going to use to filter solution. Place them together and then get the mass of both of them combined on a balance. We're going to use this value later to compare the mass collected on the filter paper after the vacuum filtration step. We're ready to do the vacuum filtration. The vacuum setup is shown here with the larger Erlenmeyer flask being connected to a smaller one to prevent liquid overflow. You place the filter that you previously got the mass of into the Buchner funnel on top, shown here, and place the Buchner funnel on top of the larger Erlenmeyer vacuum flask with the rubber seal around it. After making sure that all of the tubes are hooked up properly and sealed, you can then go and turn on the actual vacuum. Here as being the nozzle with the yellow cap. After setting everything up, what you want to do is you want to turn on the vacuum and spray a little bit of water on top of the filter paper inside of the funnel. What this does is it allows the filter paper to form a tight seal with the holes at the bottom of the Buchner funnel to prevent any of the precipitate from falling into the vacuum flask below. Sample ready by stirring it a little bit. Make sure that no precipitation is settled and stuck to the bottom. You want to carefully pour your mixture into the Buchner funnel. After pouring all of your sample into the funnel, you want to take some DI water and then rinse out the beaker that you are using. You want to pour this into the funnel as well, and you want to make sure you do it a few times to make sure that there is no leftover precipitation in the original beaker. After you've washed it out a few times, you want to let the sample sit for a few minutes under vacuum to make sure that it gets as dry as possible. You want to turn off the vacuum and carefully take the Buchner funnel off of the lever stopper. You want to take your metal spatula and then carefully remove the filter paper from the funnel and place it on the appropriately labeled watch glass. You can take the watch glass with the filter paper on it over to the heating lamp. After making sure it's not directly under the heating lamp and off to the side a little bit to prevent scorching, you can turn the lamp on and let it sit for a little while. This is your samples to make sure that they do not get scorched. Scorching happens when the paper gets oxidized a little bit and it turns brown. This will affect your mass measurement because it means that extra mass is either being removed or added to the paper itself. The sample, you can turn off the light and let the watch glass cool a little bit. You can then take the final mass of the watch glass with the filter paper and the sample. Example of the table you should write in your notebook for recording the volumes of each solution you add to the beakers. Make sure that you include space for all 4 trials and that you note the initial concentrations of the stock solutions. Also be recording your mass of the watch glass and filter paper, as well as the watch glass, filter paper, and the final product after filtration. At the end, make sure that you include the volume delivered of each of the solutions, as well as the mass of product obtained from each reaction. This is a sample of the second table you should put into your notebook. It includes the moles of each of the solutions that you added into each beaker, which is calculated by taking the volume delivered of each solution and multiplying it by their respective concentrations. Also reporting the identity of the limiting reagent of each of the reactions. This will be determined by calculating the number of moles of each reagent put into each reaction. Whichever reactant or reagent has the smaller number of moles is the limiting reagent. We're also going to be including your theoretical yield in terms of moles and mass. We'll be reporting your percent yield, which is calculated by dividing the actual yield in terms of mass by the theoretical yield in terms of mass as well, and multiplying it by 100%. We're also going to be reporting the number of moles in excess of either the calcium ion or the carbonate ion. This will be done by subtracting the number of moles of the excess reagent by the number of moles of the limiting reagent. And whatever is left over is moles of excess. This is because the moles of limiting reagent is the total maximum number of moles that can be reacted in the solution. The calcium and the carbonate ions react in a 1-to-1 fashion due to stoichiometric ratios. The maximum amount of product is going to be equal to the number of moles of the limiting reagent. If one of the substances is not in excess, you can just go ahead and write either 0 or Na. For whichever of the ions is not in excess, you may go ahead and write a 0 or Na.
Okay. All right, so the video is available if you guys need to watch it again. And so now I will break you guys off into breakout rooms randomly. And you guys can start working on your calculations together. If you have any questions, I will be here. So we have about 45 minutes left. So take a look at the sample data on Blackboard. That is where all of the data you will use is located. So let me share my full screen. All right, let's get out of YouTube. So if you it should be in the course library. If you go to course materials. No? Do you know where it's kept, Victoria? Is it in the lab sessions?
I think you have to keep scrolling down more. It was there.
Okay, sample data for lab reports. So in the course section page, the sample data and the limiting reagent. So your data is here. So these are, it starts with the volumes, okay? So volumes of calcium chloride used. So the initial and the final readings. So in this case, it would be the initial reading minus the final. Okay, because you can't have a negative volume, okay? So initial minus final. So you have the initial and final readings for calcium chloride and then sodium carbonate. The masses here are the experimental masses. So you will need to calculate the theoretical based on these readings, okay? So for trial number 1, you can use Amy and Nathan's amounts if you would like, that's fine. Or you can use, but you will need to use the sample data for trials 2 through 4 because they did not perform those. All right, so make sure you download the data. So now I will, put everybody into breakout rooms. Breakout rooms, assign automatically. All right, we have like 15. All right, so I'll make 3 breakout rooms. Let's see. Okay. Okay. All right, so I just sent all the invitations to the breakout rooms, so go ahead and join those. All right. And Victoria, you don't have to join a breakout room. It just,
Yeah. So,
yeah.
can you stop the recording? Because I was going to ask you something.
Yeah.